moving on to question 4. Let's see whether I'm going to be able to do all the other multiple choice questions into one video, or whether I'm going to chicken out and stop it halfway through so I don't have to film the whole thing again, which sometimes happens. But anyway, which of the following contains at least one double covalent bond? Double covalent bond, something like that. Should not be a difficult question. So the first one, you have C, and then you have O, and then you have O. So the first one has 2 double covalent bonds. Second one looks like this. Now this is ethene, so I have 2C, and then you have a H, and you have a H. Okay. Now if you don't know how many covalent bonds will be formed just by looking at the molecular formula, then what you need to do is to look at the position of the element on the electrochemical, sorry, I keep saying electrochemical series, which you actually don't know what it is yet because you haven't learned it. Anyway, the periodic table. So I'm just going to use the first one as an example, and hopefully at this stage you should see all of these molecules enough time that you can know automatically what type of covalent bonds should be between the atoms. But anyway, if you think about CO2, so carbon has 6, and that is so not where you're supposed to put it. Okay, 6 electrons. So if we think about electron configuration, it means that it has 4 valence electrons. And if it has 4 valence electrons, if we think about the octet rule, it means that it will want to form 4 covalent bonds in order to achieve a full shell of 8. Each oxygen has 8 electrons, and if we use the electron configuration, it will have 6 valence electrons, so it needs 2 more covalent bonds. So in order to make everyone happy, the carbon is going to form 2 bonds with one oxygen and 2 bonds with another oxygen. So if you use the same logic, you should be able to work out how many covalent bonds should be formed between the 2 oxygen atoms in O2 and between the atoms of ethene or C2H4. So the answer for question 4 is D, all of the above. Not a difficult question, hopefully. Let's move on to 5. Limitations to the electron dot and valence models of covalent molecules. Now the electron dot, as I mentioned earlier, if you listen to the video on question 1, the electron dot show all valence electrons as dot, and the valence model will show actually, let's use something as an example. So I drew CO2 just before. If I draw the electron dot, maybe you shouldn't use CO2 as an example. Oh, that's okay. If I draw the electron dot of CO2, then it will look like this. So you have to show all of the valence electrons of all of the atoms as dots. And if you draw CO2 as a valence model, then the bonding pairs of electrons will become line, whereas the lone pairs stays as dots. So looking like that. Now, it becomes a habit now. Every time I draw CO2, I will draw it in a linear shape, which is the actual shape of the molecule. However, it is not necessary for electron dot or valence model to show the shape of the molecules. So if I draw CH4, for example, I'm using electron dot model, then I can draw it like this, which it doesn't show tetrahedral as the shape of this molecule. So one of the things that it does not include, as in the limitation, is that it doesn't tell you what the shape is. So it looks like C is definitely not right, because C tells you, oh, they can tell the shape, which they don't. D is also going to be wrong because of that. Now another limitation, which, okay, it's speaking of limitation, that is a limitation of that on that side. So cannot tell shape. It definitely does not reflect the actual size of the atoms, or the relative size of the atoms compared to each other. Say, for example, in this model, carbon is a lot bigger than hydrogen. A lot. It is definitely bigger. And carbon and oxygen are also not similar in sizes, but you can't really tell. You just look at these models. So they cannot tell the size of the atoms, and they cannot tell the shape of the atoms. The answer for this is B. I think this is something that we don't really talk about very much, but you really want to be aware of the limitations of each representation that we use in chemistry, because they all representations, and they all have something that they are not representing. I mean, the obvious example here is that every atom, every molecule is a three-dimensional thing, and you can't really show it in 3D in this diagram. So that's a big limitation. Moving on to question 6. The bonding between molecules of CO2. All right, we are now entering the land of intermolecular forces by the look of it. We will talk about between. Kind of spoiled the fun a little bit by saying that. Why did I do that? When the question say between, that means intermolecular. That's a weird. Okay, I'm not gonna try that again. That's okay. Intermolecular. So we're looking at dispersion forces, hydrogen bonds, or dipole-dipole. Okay. Now, if you need to work out what type of intermolecular forces are between molecules of CO2, and very conveniently already had CO2 drawn up here, and the shape for this is linear, even though you have a difference in electronegativity. The negative poles are directly opposite of each other. The molecule itself is symmetrical, so it is a nonpolar molecule. And if it is a nonpolar molecule, then the strongest intermolecular forces present would be, hang on, the strongest intermolecular forces present will be dispersion forces. Okay, let's read this. Electrostatic forces between temporary dipoles, electrostatics between shared pairs of electrons and nuclei of the atoms. B is covalent bonds, so it's not B. Oh, okay, that's not what I'm supposed to do. Electrostatic forces between permanent dipoles, that's dipole-dipole. Electrostatic forces between permanent positive dipoles of hydrogen and permanent negative dipoles of oxygen, that's hydrogen bond. The answer is A, electrostatic forces between temporary dipoles, which are created when there is an uneven distribution of electrons in an atom that induce uneven distribution of electrons in the neighboring atom. So that's a definition of dispersion. If you don't know the definition of dispersion, though, it's actually, even if you don't know the definition of dispersion, hopefully you know the definitions of the other types of intermolecular forces and covalent bonds, so you can get to the right answer just by elimination. I think I'm going to stop here and move on to the next one in the next video.